with a non-uniform doping distribution. Well, if there is a non-uniformity in the concentration of any species, like electrons and holes and the chemical elements, the atoms, then there is a diffusion flux. There should be a diffusion flux according to the fixed first law, right? J is equal to minus D over round C over round X. That's a concentration gradient will drive the certain movement of the particles. That's what the diffusion flux is about. Okay? And if it is a charged species, then there is a drift flux, and this drift flux is sometimes it is called the conductivity, something like that, and that is related to the mobility and the electric fields. Okay? And the total flux in the situation where the charged particles are the species that is moving around, then the total flux is going to be a balance between this diffusion flux and the drift flux, right? So, for example, if it is electrons, then the total flux is going to be N mu electric field, which has been developed by the concentration gradient, local concentration gradient, okay? And that total flux should be zero at equilibrium. Right? Otherwise, there is a net flux, and if there is a net flux of certain particles in the system, we are not going to call that equilibrium. If the flux is steady, is constant, then we call that the steady state, right? But anyhow, at equilibrium, the total flux should be zero. So, the electric field, which has to be built in the system, is set by concentration gradient. And if that is an x-axis, it can be written as Q1 over P round X round P from this equation. And this is the basis for the junction properties, which is going to be discussed later. Properties. Okay? 야, 그 연락하고 있니? 안 되냐? So let me just briefly introduce the junction properties. For example, NP junctions, if we have NP junctions, then there is a junction, and before it is get contacted, then there is a certain concentration of electrons in the n-type semiconductor, and if it is contacted with a p-type, then at the very far from the contact points, then there should be an equilibrium concentration of electrons in the p-type. Okay, so this is electron concentration in an n-type, and then relatively speaking, we can say we have a very small number of the electrons in the p-type, and then that number of electrons in a p-type is going to be in equilibrium case. It can be written like that, and this P is equal to the doping concentration. So we're going to dope a lot of p-type dopants in the semiconductor to get a p-type, so that we can have a very small number of electrons. So there is a concentration gradient like this across this junctions. Then what's going to happen in between? Well, there should be a gradual changes of electrons like this, but in reality what's going to happen is that this electron is going to be recombined with the holes to get null, okay, neutral. So at the vicinity of the contact, what's going to happen is that there is no free carriers at all, because it is compensated. We don't know yet about the distance from the contact points here, this far or this far, we don't know, but virtually there is no electrons and holes at this region. There is a certain region where there is no free carriers, and of course there is a gradual changes like this. It should go like this, right? And then there is a gradual changes like that. But first approximation, we can say we don't have any electrons and holes, and inside this region, electrons and holes are going to be combined to get null, okay? And we call this a space charge region. That's the beauty of the semiconductor, right? Inside the solid, we have a very little space. This space is several microns, only several microns. So if there is a potential changes between these two regions, then we can see that it's kind of a capacitor, and the capacity is inversely related to the distance between the two conductors, right? So if this is area dielectric constant, if d is in the order of microns, then the electric field we can get out of this full potential difference between these two regions is going to be enormous, okay? And before the semiconductor era, what we have had was the vacuum tube. Maybe you guys haven't seen this, but before 1950s, okay, everybody used the vacuum tube for the amplifier, transistors, like that. And then in that, it is something like this, okay? And we call this a filament in the grid, and then we have a plate here. And between this plate and the filament, we apply some voltages, okay? And this voltages is about 300 volts. And the filament to emit the electrons, we apply usually 30 volts. Okay, and then to make emission of electron efficient, inside this tube has to be kept in vacuum. So we call this a vacuum tube, right? So everything is inside the tube is in vacuum. Now, not only physically, it is big size than the solid state transistors, but also it has to use a lot of voltages to emit the electrons to get a certain amount of electric field, which should be enough to emit the electrons in the vacuum, right? But in solid state transistors like this, if we use the junctions, the space between the filament and plate, which is the space charge region distance, okay, that is about microns, several microns only. So if we apply the 1 volt, if we can have potential difference between these two, P-type and N-type region, by 1 volt or something, then the electric field we can get is 100,000 volts per centimeter, like that. That's a very enormous thing, okay? It is much bigger than this. So the electron emission, something like that, should be very efficient under these circumstances. Now, how we can get the electric field out of this is because the diffusion flux between these two regions, due to the concentration gradient, will create the electric field which should be balanced at equilibrium. No more electrons is going to flow from here to here or here to here. No more holes is going to flow from P side to N-type side, right? Even though it has a concentration gradient to drive those movements. Okay, so that should be balanced in that sense, and then the electric field we can get out of that. This is in terms of the holes, but you can use the same word for the N-type, okay? And then same electric field is going to be built in, and we call that built-in potential. Built-in potential. This potential, we are not going to built-in electric field or built-in potentials. This built-in potential we are not actually externally applied to the device. It naturally creates inside due to the balance of drift and the diffusion flux, okay? In a metal case, we don't have this. Why? Because we cannot create any field because there are so many free electrons. But in semiconductors and insulators, we should have the balance just like this, okay? So from this base, we can have 3 very important semiconductor equations, okay? So basic semiconductor equations. And that is number one, continuity equation, and that is concentration of the flux. This is the current actually, and the generation should be equal to the concentration change with respect to time. Okay, that is the continuity equation. And transport equation, that is the current that we can get in any circumstances in the semiconductors, is going to be the balancing between the two fluxes, concentration gradient driven by concentration gradient and the built-in electric field. That should be the transport equations. And number three, there's Poisson's equations. Poisson's equations. And that says the first derivative of the electric field is going to be charge density is related to the charge density like this. For your reference, you can I just put that E naught is a permittivity in vacuum. That is 8.86 times 10 to the minus 14 Faraday centimeter. And dielectric constant, and charge density. Well, that is the basic semiconductor equations. And the next topic we have to discuss in the review, in the first chapter, is going to be about the VLSI. What is VLSI? What is VLSI? VLSI, that's a very large scale integration. Basically what it says is we are going to collect a large number of transistors in one place, and this transistors has to be separated electrically, isolated. Right? It should be electrically isolated, and it should be intentionally connected. When the transistor is fabricated, it should be electrically isolated. That is the integration. Okay? And it should be connected to get to make a circuit. For proper function, right? So the VLSI at two main process. One is build the transistors independent. It's isolated the transistors in one place, and we have to make a transistor very small. And at the end of this VLSI process, we have to develop a way to connect these transistors, which are electrically isolated. Okay, and that is the VLSI. So even though the semiconductor transistor has been invented in 1949 by three persons, which got a Nobel Prize at that time, but it takes about 10 years to get this VLSI era, okay? And this time, the main focus is how we can connect these transistors, which has been built in one place, okay? And that is going to be called metallization. Okay. Now, once we are successful in building integrating the transistors in one place, now what is the critical issues connected to this? I mean, why people say the transistors has been, the technology related to the transistors has been developed from, you started with a 64K, okay, and then 256K, and 1 mega, and 4 mega, and 16, and 64, and now we are in the era of 256 meg. Okay, why people has to develop in this sequence? Well, what we can see is that if you have 1 mega DRAM in this size, okay, we have 1 mega DRAM. Then why people cannot make 4 mega DRAMs with 1 mega DRAM technologies? That is my question. Okay, if we make the size 4 times of this, and then make 1 mega, 1 mega, 1 mega like this, then it's a 4 mega DRAM. Then why people in the era, I think 1 mega is only 200 year 20,000. We try to build 1 mega DRAMs. And people cannot make 4 mega DRAMs at the time. It takes about 2 years to be successful industrially to make 4 mega DRAMs. Now why it takes 2 years? All you have to do is just put 1 mega DRAMs or 4 of this in the same place, and then we can say we have integration technology for the 4 mega DRAMs. Why people cannot do that? Why industry cannot produce this thing? And that's because it has been shown in the text. Let's say this is a silicon wafer, okay? And you cannot make a perfect single crystal wafers if this size is considerable, larger than the 6-inch, okay? And then maybe inevitably you can have certain number of defects, something like this, okay? And if you have a technology for 1 mega DRAMs and the size of this is this much, okay, and then the yield is going to be something, okay? Let's say it's on the note, but let's say your die size, we call that die, by the way, is something like this, okay? Then probably we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, something like that, okay? So we have a certain number of yields. But if you increase the size like this, then probably you can have only 4 of this out of one wafer, then the yield should be 0. Okay? So the guy who can make a 1 megadirhams, he cannot make a 4 megadirhams commercially because the yield kills everything. His yield is very low, and then the chip should be very expensive in this case. So if you want to say, I can make a 4 megadirhams, then means that you can have a very high yield, as much yield as you had for the lower integration levels. Only in that case you can say, I can make a 4 megadirhams and 60 megas, 40, 64, something like that. So if we say we are in the era of 256 megadirham era, it means that the yield is more than 90%, which means we have to make this huge integration, this high integration level at a very small size. What does that mean? We have to make a transistor small and small to get that large number for integration, right? So these days, for the 256 megadirhams, the gate size, transistor size is sub-micron. Sub-micron. We call sub-micron era. Because the gate length, which is critical for the total transistor length, the gate length is a kind of criteria to call the size of the transistors. And then the gate size is less than 1 micron, and it's a sub-micron. In order to have 256 megadirhams, and because we have to keep the die size such and such to make the yield high, right? That's pretty much related to that. So whenever people say, why we cannot make a 1 gigadirhams? If you collect just 4 of this, then probably we can build 1 gigadirhams. Then people are not saying that we can make 1 gigadirhams, right? So, if you want to make a higher level integration than 256 megadirhams, then you have to develop a very, very special techniques which are not used currently. Like for the lithography, currently we are using a ultraviolet light, okay? But we have to have a very short wavelength light to have a resolution good enough for 1 gigadirhams. And that has not been developed yet, okay? So we should say we cannot make 1 gigadirhams. Will you check again? Oh, so can you turn it on? Load the.
이게 일로 옮겼니? 이거 뭐야? 이거 왜 이래? 안 돼? 아, 오케이.
In the note, it has a description about the basic operation memory devices as on page 48. And you can see, let me just review that a little bit. Here. What happened to this? I cannot see the images. Okay. We have DRAMs and SRAM, and it is not on the text, the flash memories and FRAMs. So let me, you just turn it off. Let me, 어디 갔어 얘? How can I up this? Stand by. Turn on the light. The memory devices. First, the DRAM, dynamic random access memory. Okay, dynamic random access. In the DRAMs, it is called the random access because it's kind of a matrix, okay? And if you want to pick up some one point, then all you have to do is you are going to have some certain number in x-axis and a certain number in the y-axis, then you can pick up the one point directly. In old days, we have a recording tape. Okay, if you want to listen a specific song, which is in the middle of the tape, then you have to wind up to reach that position. Okay, and that is not a random access. Okay, in a CDs, for example, in a chips, if you want to hear the song which is recorded, memorized in the middle of the memory, then you can just put the number for the X and Y and then you directly go there. That is a random access. Okay, so DRAM is dynamic random access memory, and then each point we have transistors, okay, and that the transistor is going to look like this. This is a MOS transistors, and then each transistor is connected to the capacitor, okay. So one capacitor is connected to each transistor, and that is 1 bit of DRAM. All right. The problem with this DRAM is, firstly, number one, there is a leakage. It has the information memorized because of using this capacitor. If you put the charges in there, then it should be there. But as you know, the capacitor, it loses its charges, naturally releases the charges. So there is a leakage of the charges, the information. So you have to regularly, refreshment is required. That is why this memory is going to be called dynamic. Usually when you say dynamic, it is somehow we have a feeling that it is something good, right? But this dynamic is not good. This means we have to refresh the memories, the capacitors, okay? When the charge is below 0.5 levels, for example, then you have to flash it again to get 1 to 1. Okay, so that's why it's called a dynamic random access memory. And so this is the volatile. We call that volatile memories. So there's a problem. If you want to memorize some addresses or telephone numbers in your handphone, for example, then you cannot use the DRAMs in your handphones. If you use the DRAMs, then when you change the batteries, then all the information is going to go away. So this volatile memory cannot be used for the handphones and mobile devices. It can be used only the desktop, which should be connected to the wall. Okay. And another type of the memory device is the SRAM, static random access memory, and that is static random access memory. And how do this memory works is that you connected two MOS transistors like this, okay, and then one of this is a PMOS and one is the NMOS, for example. We call this inverter. Then it's a kind of a input and output, always the opposite. That is the function of this inverters, okay? And then you connected two of this, and let's see, if you want to draw it, you may draw one inverter here and then the other inverter. you use two inverters, and then those two inverters should be connected to get the VD and VC, VS, and then to control, you want to connect to this each part with another transistors to make a good switch of this, okay? And then you use 6 transistors to get 1 bit in the SRAM. The beauty of this SRAM is that the leakage is minimized. You cannot avoid totally, but you can minimize the standby current. We call that the standby current. Standby current. So no capacitor is required. That's not a trivial thing at all, because this capacitor, how you can make this capacitor? You can make this capacitor by putting 2 conducting plates and separated by some dielectric materials, like silicon oxide typically, okay? And this conducting 2 plate is a heavily doped silicon. You use a heavily doped silicon, which is almost the same to the metal in terms of the conductivity, okay? Use two things, and it should be separated by the silicon oxide, the thin films. Now, we just discussed a minute ago, the capacitance is related to the area, okay, is inversely proportional to the distance, but is proportional to the area. So, for have a minimum requirement for the electrical properties, you have to use some of the areas which is very, very expensive in the VLSI. When it becomes a 256 mega dirhams, then it has been built on the 2-dimensional silicon surface, you should say, so that each area is very, very expensive. And then you have to allocate some of the areas to this capacitor, then that is really painful, okay? Now, if you move to the static RAM, then you can omit this capacitor, but because you can minimize the standby current, but you have to use the 6 transistors for 1 bit. This is 1 transistor for 1 bit. So integration level is not going to be enhanced normally. There's not much difference. And in terms of the process, you have to have NMOS and PMOS at the same time, so that we call that the CMOS, complementary MOS, complementary MOS. So the process becomes very complicated. Say if you use a P-type wafer to begin with, then what you have to do is you have to, at the surface, you have to have a field oxide for the separation of the transistors. Okay, and then you have to build some areas, we call that this N well. You have to build a well to have a PMOS in here. P plus and P plus, we call this the PMOS. you cannot build a PMOS on the P-type substrate. So the other areas is going to be, it's going to look like this. And this is the N plus and N plus. And this is the NMOS. Now, as you can see here, the process becomes very complicated to get a static memories. But in most of the VLSI structures, 256 mega DRAMs, for example, we usually use the DRAM. One transistor, one capacitor for 1 bit, okay? And very special logics, we use SRAMs. We have to minimize the standby current, even though it kills the integration levels. Now, we have another kinds of memories, which is flash memories. All these DRAMs and SRAMs are volatile memories. Anyway, it's a volatile. So for non-volatile memory devices, we need this. Why? Because we have to have a mobile devices everywhere. For the handphones, we have to have a non-volatile memories. Okay? We has a technology for the flash memory, and this flash memory is nothing but a source and drains, just like a DRAMs, but it has a one more transistors, something like this, so that this is a gate, as in most transistors, and we call this floating gate. And when you make this a floating gate, you make you are not going to make this gate oxide uniformly, but you have a very shallow, you are going to make very shallow, very thin gate oxide. Gate oxide, SiO2. So if you want to write anything to this flash memories, what you have to do is you have to increase the voltage a little bit more so that some of the electrons is going to be injected to the floating gate. And it stays there. And these electrons is not going to come out. So there's a shallow gate oxide. So that it is not going to be volatile anymore. It's kept there. So when you memorize one thing, then it should be there. So it doesn't need a capacitor. Okay? So it is good. But the problem is it has a terrible programming speed. Programming speed is very, very slow. Like, let me give an example. When you have a memory, usually you have a writing speed and erase speed. Okay, erase. We'll call that, instead, let's say, reading speed. Okay, and then DRAM is 50 nanosecond, and both of them are 50 nanosecond. But for the flash memories, this is a 10,000 nanosecond. Okay. The reading speed is almost the same, but the writing speed is this slow, so that it cannot be used for the programming. It just flash memory can be used only for the storage. So flash memory is only good for storage. Not for programming. But it has done a tremendous change in the industry because all the memories has been the non-volatile memories we have been used for the magnet for the non-volatile memories. So you haven't seen this on the video, that if you have a supercomputer, then it has a magnetic tapes. All the time you use the tapes for the computers, even these days, okay? Because the magnetics are the only thing for the non-volatile memories before the flash memories. But after the flash memory comes, then this flash memory try to replace the magnets, okay? And then next time on the Wednesday, we're going to discuss about how these flash memories change the devices and what kind of revolution has been brought about through this invention of the flash memories, and what is the drawback, what is the limits, what kind of things that we have to do for the future to overcome the drawbacks of these flash memories. Okay? So I'll see you on Wednesday. Any discussion, any questions? No. That's good. Okay, I'll see you on Wednesday then.